All right, welcome again. Welcome to the next installment in the kind of getting started guide for embedded systems and microcontrollers. And this video, we're going to spend a little bit of time talking about some design tool concepts. So we spent some time going over what a microcontroller is and looking at kind of how it works from a high level view and what types of interfaces you would have. We've also kind of looked on what's inside of that microcontroller, what to expect and what you're going to see in like the generic microcontroller. For example, our, Acme Mark One, brand, microcontroller. So what I want to do here is go over some concepts in how you actually work with these devices, keeping in mind that we're not going to actually do any programming right now, but I want to get some concepts, in your brain. So when you do go to use these tools, you have some context. You can see the big picture. Probably one of the other most difficult things about getting started with microcontrollers is using the design tools and understanding how they actually relate to making that controller work. Because most design tools are not written for the novice, they're written for the advanced user. So it's really easy to get lost, especially when all you want to do is make something simple work. So what I'm trying to introduce you to here is what you need to know so that you could kind of approach any design tool, and get going, or at least kind of get started. So I kind of peeled off the top, and we're going to look at this generic microcontroller again. And what I want you to look at is to understand is that we have this core that executes instructions, and that's what essentially makes everything work. So to toggle GPIO, to get data out of this pin, to kind of communicate over a serial port, we need this CPU executing instructions, in getting instructions from either RAM or this flash memory. But that makes the assumptions that we have instructions in here, the actual like binary codes that translate into the move instructions, the add, whatever that microprocessor is supposed to do. So the idea of a design tool is to kind of take our design files and get them in a format so we can get into this flash memory here. And the way that's usually done is through, the debugger. Now, it doesn't always have to be. There's other ways we can get, this binary code into the flash memory, but it's often done through the debugger because there's a lot of neat stuff that you can do with the debugger. So keep in mind, that is the end game of all these design tools, is to be able to generate binary codes that the CPU can execute to make your project work. Now, to get to there is sometimes, rather complex. And hopefully in this video, I can break it down in a fairly simple way that it's really not that bad. And when you subtract out all of the marketing done, by companies who make the IDE, all these complexities, there's really not a ton to it. But keep in mind, we're just trying to go from, kind of like a high-level design, specification on the PC in the form of our code and get it into that flash memory or RAM so we can, test, debug, and deploy, our software. So on the right-hand side of the screen, I have an example of, assembly language, or ASM for short. So you might have seen this in a computer organization class. All assembly language is, it is a set of, it's a representation of the binary, instructions of the instructions that the CPU can execute. At the end of the day, all of these instructions map to some sort of code. So for example, a push instruction and I'm just completely making this up, might be a 0xAA, indicates the push instruction. The add might be a 0xAB. So assembly code is a little bit higher level way of writing down, the instructions for that core, in a way that humans can kind of understand. At one time, you actually wrote in hex or in binary, but kind of the first tool that was made was what's called an assembler that does some of that work for you. It makes it easier to read. You can put in nice labels. You can put in other, directives to where you want to align data, and where you want to put your code. But you're at very, very low level. No one almost rarely does this. The design tools. Some people still do assembly language. There are still, good uses for assembly language. But more often than not, most of the time, we work in, a high level language. And what do we mean by that? So a high level language is any language where we are coding behavior, not necessarily specific implementation. Now, the line is fairly gray there, but a high-level language does not necessarily but you are not necessarily coding for a particular machine. You're coding for a behavior. So, for example, when I say counter equals 0 right here, I'm not necessarily concerned about the machine language or the assembly language instruction. I just want a variable, an integer in this case, and I want to assign it 0. I don't care how that gets done. And that's the idea of the high-level language. We want to specify what behavior we want. We don't necessarily care how it gets done in the architecture. For example, counter plus plus, this is C code, says increment counter by 1. Well, in this case, for example, this is, this might translate into the add instruction. Now, your particular architecture might have different add instructions or might be completely different. But at the end of the day, the high-level language is where we work because we want to specify behavior because we can get work done faster. When I say faster, I don't mean it executes faster. I mean we can get our task done because working in assembly language is a little more difficult. Now, to go from this code to this code, we need a compiler. In some cases, we use what's called an interpreter to do it in real time, but we want to take this code and generate the actual assembly language for, a particular device. So that's the word you're going to hear. We need a compiler for our high-level language. Now, I wanted to this is a very, very recent slide, 2013 embedded market study, done by UBM. They run the Design West, what used to be called the Embedded Systems Conference. So anyone who's anyone goes to the Embedded Systems Conference. It's a collection of vendors, engineers, and they do surveys of what's going on in the embedded system space. And every year they take a lot of surveys. They see what people are doing. They kind of get the feel of where things are at. And I wanted to show you this. And especially if you're kind of new to microcontrollers and embedded systems, to see what people are using kind of in the real world. And I want to give you some context here from my experience. The first thing notice is that the language C, overwhelmingly, embedded project is programmed in C. Followed by, kind of far behind, is C++, which is an object-oriented kind of, I'll say version. It's a lot more than that, but say it's object-oriented C. And if you don't know what object-oriented means, you can go to Wikipedia, discover it for yourself. The next is, assembly language, what we were discovering before. Still people use it. Then all these other languages down here. Now, let me put this in context for you. Assembly language C and C++ for what I call true microcontrollers, what I call bare metal microcontrollers where there's no operating system, no nothing. That's what it is. Java, in the case of Java, I can almost guarantee you this is not for what I call a microcontroller for, say, an engine control unit. This is definitely for some sort of like application processor, say on a cell phone. C# is essentially Microsoft's Java. That has to run on some sort of PC-like hardware or an environment that allows their .NET Micro framework. That's a very high-end system. It's very slow but very high-level language. MATLAB, the same. That normally runs on a PC. I don't even know why they included that or someone wrote that in. But in most cases, if you did something in MATLAB, you used some sort of tool to generate C code, which then generates assembly language. LabVIEW, once again, that is probably they have tools that are used to generate C code, or they have certain very closed platforms that you can program in LabVIEW. Python is an interpreted language, as is Java and C#. It's not compiled. It's interpreted. .NET, it's interesting. They didn't distinguish. C# and .NET are fundamentally the same thing. And others, God knows what. So Ada is, a very old language. It's been around for a while. Used actually quite a bit in the government. But your takeaway here is if you have to learn one thing, C is it. Now, you're going to see assembly language and you do embedded programming. You yourself might not be coding it, but you're going to see it. C++, as 32-bit controllers come online, it's a little bit easier to take advantage of C with 32-bit controllers. Not to say you can't do it with 8 or 16, but you can start getting away with some of these higher level design concepts and not because you have the CPU horsepower to handle it. And you'll slowly maybe see some of these other ones with microcontrollers, but everything, kind of from here down is what I'd call essentially an embedded PC or some sort of like very high level system. So that being said, if there's one book you could have on your shelf, this is it. This is written by the guys who came up with the C language. This is also what they call KNRC. So the second edition is what you want. It was written a long time ago, but the concepts in that book still apply. Pointers, structures. Now, there's certain things you might not have in your system. For example, they reference Unix function calls for accessing files. But what you see in there is so ubiquitous it's so good. If you're going to learn C, you should have this on your shelf. I would highly recommend if you don't have this and you want to do C programming, I would say if it's not in here, it doesn't exist. This is standard, C language. Now, most of their examples are for programming like a Unix workstation or, say, a Windows PC, but it's the reference for embedded programming as well. So what is the typical flow, with your design tools? So step one, we need to compile. And whenever we talk about compile, this is where we talk about, the term source. Compile from source, meaning the source code. This is not the low level, the code that's executed on the machine. We call this the source. You take your source code, and what most compilers do is they generate assembly code, actually assembly code for your particular architecture. Because you can take one piece of C source code and compile it or cross-compile it to many different architectures. We go through a step called linking. What linking does is, if you have many source files, you go to many assembly language files. Well, it takes all those different the outputs of all those assembly language files, what's called object code, and then links it into one final, what we called binary. In the binary is a file that'll sit on, say, your PC and with your dev tools that actually contains executable code. Now, your binary might, depending on the format used, such as L for cough, may have debug information where it links up, okay, this variable's at this address. But at the end of the day, that binary is run through a set of tools that generates an actual image of what should be in your flash memory. All right. So the output of that, you'll use a design tool to download to the flash and once you download, you run the debugger. Now, it's very possible to skip that debug state and simply you compile, you assemble link, and then you download and go. But the debugging is so ubiquitous now. It really makes sense to have the debugger because you can once again set breakpoints, you can stop the code, you can look at it. But this is the typical flow, and this is what you need really to have a good setup. Now, it might seem like there's a lot here, but usually what you do is you get a tool called an IDE, an Integrated Development Environment. All an IDE is simply it puts together your compiler, your assembler, your linker, all the tools to download and debug in one package. And probably most of the complexity that and most of the trouble people have is understanding these IDEs because they can be complex. But if you keep in mind, that is the flow: compile, assemble, link, download, debug. That's what you're doing. You're going from the compiler and you're trying to get stuff in the chip. So here's an example of an IDE. This is Freescale's Code Warrior, and Code Warrior is based upon a tool called Eclipse, which is used to build IDEs. And you can kind of see I have my code here. I can see my assembler. What's cool, I can see a value of this counter. I can inspect registers, look at stuff down here. It kind of puts this all into a view that, for example, I have a go button. You can single step and step through code. This is what an IDE does for you. It makes your life much easier. Now, you need a way of getting code on the chip. Now, on the right, this is a P&E multi-link. So, in one side, it has USB. On the other side, there's a cable that has either JTAG, which is the standard. It can do Freescale's BDM, BDM, and some other interfaces. Now, I showed you on the left, this is actually the Freescale, and it's kind of abbreviated FRDM, Freedom Board. Like most dev boards you get, whether it be from Freescale, Microchip, Renesas, TI, they'll sell you low-cost dev boards that actually give you the microprocessor, but they'll integrate logic that has the debugger. So in this case, this has an interface called OpenSDA. And it's just a debug interface that allows you to plug in the Code Warrior and do all the code downloading. So I think, for example, this is a $13 board. There's boards that are $50, $100, but more often than not, they'll have the debugger built in. So you kind of use this, in development, where whenever you make your own circuit board and you put your own chip on, you'd use something like this to do the downloading. Now, that doesn't preclude you from getting the code in there some other way, say through some other sort of bootloader. That OpenSDA, in addition to having a debugging interface, also has a nice drag and drop bootloader, but you can't debug with it. Some other options. There's starting to be more prevalent the concept of online integrated development environments where you don't install to a PC. It's in a web page. It's essentially a JavaScript application. And if you go look on the internet, there's something called Embed, and it actually works with the Freedom Board. It allows you to do all your compiling on the web. It does not allow you to debug. That's what you need to have what's called an offline tool for. But it is a nice option if you don't want to install anything. Now, you don't have to use C. You can use non-standard languages based upon C. So in the hacker community, Arduino is popular. It's a C-like language. It's kind of like it tastes like chocolate. It looks like chocolate, but it's not chocolate. It's something else. It's usually easy to get started. You don't have to use an IDE. You could find a compiler for that chip. You could do everything manually. But generally speaking, industry, meaning the people who make cars in the world, the people who make stuff, they use C or C++ with offline tools. That is the standard flow. So final notes, you don't have to go that route, but more often than not, if you learn this, you're covered. Have fun with the offline tool or online tools like the Mbed or the Arduino, but keep in mind, when you want to get down and dirty, that's how it's done. The other thing is, don't design your first board from scratch. Use a dev board like the Freedom board. Freescale's a tower board. Microchip has tools. TI has tools. And all these tools are plentiful and free. A lot of times they're based on open source compilers like GCC, but the idea is you don't have to build this stuff from scratch. Use the tools that are available. When you pick out a platform, you may pick based upon a low-cost tool like the Freedom to get started. It really doesn't matter. Find something that you can afford and make it work. Find a project that you can make things work. And I can guarantee you, for less than $50, you can find anything you could possibly dream of, 32-bit, 16-bit. And like I said, in the case of Freescale and the Freedom board, it's $13. You cannot go wrong. It's like candy. You buy it and use it and eat it. So I hope this kind of clarifies design tools. So in later videos, we're going to dive into some of the design tools, but I kind of want to give you this perspective of this is what you're doing. You're compiling. The compiler in the back end goes to assemble, link, you download, and then you debug. I don't care who makes it or who puts their stamp on it. That's what you're doing. So, all right. So I hope you learned a little bit, and tune in for more videos.